Hi guys, so today we're going to find all irreducible polynomials of degree 2 in a ring of polynomials in modulo 3. So let's break down this question a little bit further. What are irreducible polynomials? So irreducible polynomials are polynomials that cannot be simplified or factored further. So for example, I have here x3 plus x. And you can factor that x out and you get x squared plus 1. This is considered a reducible polynomial because you can factor it. Or I have here x squared plus 2. You can't factor or simplify this further, so this would be considered an irreducible. And then what about this z3? All the integers in modulo 3. So in z3, we're going to have 0, 1, 2. So there are 3 integers in modulo 3. So first, let's write down the standard form of a polynomial of degree 2, and that would be fx is equal to x squared plus ax plus b. So how did I get this? So first, it is degree 2, meaning that the highest power in our polynomial equation should be 2. So we have here 2. These are the coefficients of the polynomials, a and b. And for a and b, those will be in mod 3. So these coefficients can only be the numbers 0, 1, or 2. Next, we need to find all the polynomials of degree 2 in mod 3. First, we're going to have to find all the combinations of a and b. So what do I mean by that? So for example, let's let a equals 0 and b equals 0. Where did I get that? A equals 0, b equals 0. And let's do that for 1 and 2 as well. So a equals 1, b equals 1, a equals 2, b equals 2. Let's also do the combination 0 and 1. A equals 0, b equals 1. Let's also do a equals 1 and b equals 0. Let's do 0 and 2. A equals 0, b equals 2, a equals 2, b equals 0. Let's try the combination 1 and 2 now. A equals 2, b equals 1. So as you can see, we have the combinations. And a way you can check that you have written all the combinations of a, b is by taking the given number for the modulo. So we have here 3. And then take it to the power of the degree that you were given, so degree 2. So there should be 9 possible combinations of A, B. So let's check that. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know for sure that we had created all the possible combinations of A and B. Next, let's plug A and B into the polynomial equation. So fx is equal to x squared plus 0x plus 0, and that is equal to x squared. Second one, fx is equal to x squared plus 1x plus 1 equal to x squared plus x squared plus x plus 1. X is equal to x squared plus 2x plus 2. That's equal to x squared plus 2x plus 2. So now I'm going to do that with the rest of the ABs. So now that we have all of our polynomials of degree 2 in modulo 3, now we need to figure out which ones are irreducible. And in order to do that, we need to know which one has roots and no roots. If the polynomial has a root, then it's reducible. However, if a polynomial have no roots, then it's irreducible. So how do we determine if the polynomials have roots or no roots? Well, let's do the first one. What you would do is let x equal 0, and I let x equal 0 from z3 here. 0 squared, which is equal to 0. Once there is a 0, you know there's a root. So this makes the first one reducible. So let me add a bullet point here that it is reducible if y is equal to 0. All right, let's continue the next one. So again, let's make x equal 0. 0 squared is 0 plus 0 plus 1, which is equal to 1. It's not a zeros. However, we still have to keep going. Let's make x equals 1 now. So f1 is equal to 1 squared, 1 plus 1 plus 1 equal to 3. However, we're in modulo 3, meaning that if y is divisible by 3, it automatically goes to 0, or it's congruent to 0. And since it's a 0, this polynomial is also reducible, right? Let's keep going. So again, f is equal to, plug that in, 0 squared plus 2 plus 2 is equal to 2. This is not a 0. You have to keep going. f1, so 1 squared is 1 plus 2, so that's 3 plus 2, that's equal to 5. That's not divisible by 3, so again, we're still in the clear, but we still need to check f2. So what is f2 here? 2 times to the second power is 4, plus 4 is 8, which is equal to 10. 10 is also not divisible by 3, so we're sure that none of these have 0, so we can conclude that this polynomial is irreducible. Let's do the next. So f0, 0 squared is 0, 1, that's equal to 1, not 0. Let's keep going. f1, again, from here, 1 squared is 1, plus 1 is 2, not 0. Let's keep going. f2 from here, 2 squared is 4, plus 1 is equal to 5. Everything is not 0, meaning that this is also irreducible. And remember, irreducible meaning that it has no roots. Let's keep going. f0 is equal to 0 squared plus x, 0. Already there's a root, so this is reducible. All right, f0 is equal to 2. f1 is equal to 3. This is divisible by 3, so it is congruent to 0. We reach 0, so this means that this is reducible. Going already 0 plus 0. We have a root, so this is reducible, right? f0 is equal to 2. Keep going because this is not 0. f1 is equal to 4. It's not divisible by 3, so we can keep going. 2, that is 4. 8 is also not divisible by 3. So this means that this has no roots and is irreducible. Last one, f0 is equal to 1, not 0, so let's keep going. f1 is equal to 1 squared equals 1 plus 2, so that's 3 plus 1, that's equal to 4. Non-divisible by 3, so let's keep going. That's 9. 9 is divisible by 3, so that means it is congruent to 0. As a result of it being 0, it means it has a root and it is reducible. Therefore, we can say that the irreducible polynomials of degree 2 in modulo 3 is x squared plus 2x plus 2. Another irreducible one here, 2x squared plus 1, x squared plus x plus 2. All right, and that would be our final answer. 1, 0.